Let's talk about homomorphisms of modules. So suppose R is a ring and M and N are two R modules, so they need to be modules over the same ring R. Then a map, a function from M to N is said to be a homomorphism, and sometimes we call it by other names. We sometimes say it's an R linear map. It's another word for homomorphism, or if we want to emphasize the ring R, we sometimes call it an R homomorphism. Okay, so there are sort of many different words we use for this. So a homomorphism of R modules is a map satisfying the following two properties. One, that f of x plus y equals f of x plus f of y for all x and y in the set M, and property 2 is that f of R acting on x should be R times f of x. So this is the for all x in M and for all ring elements R in R. Okay, so in other words, a module, remember, has two important operations, that of addition and scalar multiplication by the ring R, and a homomorphism is a map which preserves these two operations. Okay, now so what are if you sort of look carefully at this definition, notice that this plus here is the addition in the space M. This plus on the right is the addition in the space N. Similarly, if I take this scalar multiplication here, R dot x, this dot is scalar multiplication in M, and the right hand side is scalar multiplication in N. Okay, now one quick observation: if you forgot for the moment that the modules had a scalar multiplication, just think of them as abelian groups under addition. Then a homomorphism, if you just look at property 1 alone here, in particular a homomorphism of R modules is in fact a homomorphism of the underlying abelian groups M and N. Okay, so observe that this property 1 says exactly that f is a group homomorphism of the group abelian group M plus to the abelian group N plus. Okay, it's a group homomorphism from M plus to N plus. Okay, now property 2 of course says that in addition to being a group homomorphism, it also respects the scalar multiplication. Okay, now let's look at examples. So this must be a familiar notion from linear algebra, a map which preserves addition and scalar multiplication. So this is what we call a linear transformation, right? So if R is K, a field, and if M and N are R modules, therefore they are K vector spaces, then a homomorphism is exactly what we would call a linear transformation. F from M to N is an R homomorphism, means that F is a linear transformation of these two vector spaces. Okay, so it's just that familiar notion sort of imported to the context of modules over any ring. So that's the first example. Now here's a quick remark. So of course all these were defined for left modules, but there's it's not surprising how one defines homomorphisms for right modules. You just demand that it preserves the scalar multiplication on the right. Okay, so remark, if M and N are right R modules, then a homomorphism is a map such that it preserves addition as before, and it preserves sort of the right scalar multiplication. So recall I sort of spoke about this notational convention for right modules. We often think of it as the scalar sort of multiplying on the right. Okay, so f of x dot r is f of x dot r. So if you have a map satisfying these conditions, then you would call it a homomorphism of right modules. Okay, now let's look at more examples. So I talked about example 1, which is that of vector spaces and linear transformations. Example 2, so a general class of examples, if n is a submodule of M, if n is a submodule of M, then the inclusion map, so from n to m there is what's called the inclusion map, it's called I, which does the following: it takes each element to itself. Okay, so it's just n is after all a subset of M, so any element of n is necessarily an element of M as well. So the inclusion map is obviously a homomorphism. In fact, it's sort of trivially a homomorphism, because the x plus y of course goes to x plus y, rx goes to rx, so the properties are obvious. So in particular, if I take n equals m, then the inclusion map becomes what's called the identity map, right, which takes every element to itself. So this is usually denoted as id or id sub m. This is of course a homomorphism too. Okay, so the identity homomorphism or the inclusion homomorphisms. Now example 3, let's take the same setting as before. If n is a submodule of M, if n is a sub of M, by which I mean submodule, then I consider the quotient. So recall we talked about the quotient m by n, which is the set of all cosets of n in M. Now from M to the quotient I have what's called the projection map, okay, which is, what does it do? It takes each element x of M and maps it to its corresponding coset x plus n. Okay, so this projection map is a homomorphism. Okay, let's check this quickly. This just follows from the way the addition and the scalar multiplication are defined on the right hand side on the quotient. So let's check that pi of x plus y. So what's pi of x plus y? It is x plus y plus n. It's just the coset of the element x plus y. But if you recall the definition, this is exactly how addition is defined in the quotient module. Okay, now pi of rx similarly is just the coset of rx, but again by definition that's exactly how scalar multiplication was defined on the quotient module. Okay, so these two equations here establish that this map pi is in fact a R module homomorphism. So we have these natural classes of examples, the inclusion and the projection maps. Now let's look for other examples. So example 4, if we have a ring, if we take our ring R to be the ring of integers, then recall that if I have two R modules, so Z modules are the same as abelian groups. Okay, this is the same as saying that M and N are really abelian groups. Okay, and what is a homomorphism now from M to N? Okay, so homomorphism is supposed to satisfy two properties: f of x plus y is fx plus fy. In other words, it's a group homomorphism, and it should satisfy this compatibility with respect to all x in M, compatibility with respect to scalar multiplication by elements of Z. But observe that this second property is superfluous. We don't really need this one. If the function satisfies the first property, that f of x plus y is fx plus fy, then the second property is automatically true. Okay, this implies the second one automatically for Z modules. And why is that? Because recall that f of, so if r is an integer, so let's say for the moment let's suppose r is a positive integer, then recall that this scalar multiplication was just repeated addition. So you just had to add x with itself r times, right? This is how we defined it. And if the first property is true, it means f of x plus x plus x is the same as f of x plus f of x plus f of x those many times. This is just by using the first property alone, that it is a group homomorphism. This implies this, but that's exactly the definition of how the element f of x is scalar multiplied by r. Okay, so of course I will just leave it for you to check that the same sort of thing holds if r is negative or 0. So what this really says is, recall we said if a Z module is essentially the data of just the abelian group. Okay, the scalar multiplication is defined in terms of the addition. And for homomorphisms, a similar thing holds. A homomorphism of Z modules is just a homomorphism of the underlying abelian groups. The compatibility with respect to scalar multiplication just follows naturally as a corollary. Okay, so that's the fourth example. Let's do our other standard example, which is the ring Kx of polynomials or in one variable x, so where k is a field. And here again we know what, so let's say M is an R module, and recall that modules over the polynomial ring Kx are the same as, well, what is it? It's like having a vector space V together with a linear operator on it. Okay, so where V is some vector space over the field K, so it's a K vector space, where V is the K vector space and T is from V to V is a linear operator. Okay, and recall again from all our previous lectures that the element x, the polynomial x, acts as the linear operator T. Okay, now similarly let's take n, that's also given to be an R module. So let's assume that n corresponds to the pair W comma S, where W again is a K vector space and S is a linear operator on W. Okay, so now what we are going to do is to try and figure out what it means for a map f from M to n to be a homomorphism. So suppose I give you a homomorphism of R modules, of Kx modules. So suppose f from M to n is a homomorphism of Kx modules. Okay, so what does that mean? Okay, so let us check what it means. Now let's go to the next page. So observe that it just means that I have the additivity property. So this means two things. Number one, f of v1 plus v2 for all v1 and v2 in V. So notice that when I say M and N are given by V and W, so V and W, recall, are the underlying spaces. So I should probably just replace M and N by the underlying vector spaces V and W. Okay, so the set is V and W, and I have a map between them which satisfies these two axioms. Number one, f of v1 plus v2 is f(v1) plus f(v2). So this is the additivity. Second property is f of rv is rfv. Okay, so let's try and analyze what the second property means. So we'll try and understand this. So let's do the following. We'll start out by, so first let's take, so case A, let me take R to be an element of the field K itself. Okay, R in general it can be any polynomial, it's an element. So remember, this is K of x, so I should put in all polynomials in x there, but for a start I will just take the constant polynomials. Okay, so take R to be a constant polynomial. So in this case I know that this is true, that f of RV, so which implies I conclude from property 2. So property 2 in particular implies that f of RV is RFV for all constant polynomials. Okay. Now what does this mean? This says that if I multiply V by a scalar from the field K, that scalar can be pulled out. Okay. Now let's analyze this property. So I have this guy together with the additivity with the first property. So now put these two together and let's stare hard at it. What does it tell us about f? It says that f is a linear transformation of the vector spaces V and W. Okay, so this the two properties I have marked in green are exactly the definition of f from V to W is a linear transformation, okay, of these vector spaces. It's a linear transformation of the K vector spaces V and W, okay, or V to W really. Okay, so that's only part of the data. We haven't used the full force of the hypothesis. We have concluded that at the very least f is a linear transformation from V to W. Now let's do still more. Let's also take the polynomial x here. So far we have taken R to only be the constant polynomials. So case B, let me take for R, I will take the polynomial x power 1 or x. This is of course a valid choice of scalar, it's an element of the ring. So now I will plug this in and see what I get. So remember, f of RV is the same as RFV for all V in V. So this again is for all in V. Now what does this imply? Since R is x, this means that f of x acting on V should be x acting on FV, and recall that the action of x is exactly given by the action of the polynomial by the operator t. So this is the same as s acting on FV. Okay, so this last equation comes from realizing that the actions, so this data here exactly says that the polynomial x acts as t and the polynomial x acts as s on V and W respectively. Okay, so now let's unravel this a little bit more. So we have concluded the following, that I have this operator f, it's a linear operator from, so f is a linear transformation, and second property I have concluded is that f composition T is the same as s composition f. Okay, so that's what this last equation says. F of TV is the same as, so this equation here is just saying that f composition T is the same as s composition f. Now let's try to figure out where these compositions really live. So remember, T is an operator from V to V and S is an operator from W to W. So what does this say? It says that f composition T is the same as s composition f. Okay, so let me think of it as follows, that let me draw T in the opposite direction. It's a map from V to V. So let me think of it as going like this. So now observe, what am I saying? I'm saying that whether I so if I look at, so maybe I should put the f here. Okay, good. So let me now draw it in the same direction so that this diagram is slightly more symmetrical. So I will draw the diagram in this way. So let me just put one more additional f on the bottom. So what I have drawn is a diagram of these vector spaces V and W, a little square of maps. Now let's observe what this equality says about this diagram. So it says that if I look at f composition T, means I first come along T and then go along f. So it's this way, I come from V and go down to W. The other side, s composition f, is the other path. I first do f and then I do s. Okay, so what this identity is telling me is that whether I go along this L here or this inverted L, I get the same answer. Okay, so this particular diagrammatic way of understanding such compositions. So we usually say that this diagram commutes. So we draw this diagram, and when we say this diagram commutes, it just means that whether you go along one path or the other path, the answer is the same. Okay, and we usually put this little arrow here to say the diagram commutes. Okay, so this is really what a homomorphism is between two kx modules. We have concluded that it must be a linear transformation which makes this diagram commute, which is such that f composition T is the same as S composition F. Okay, and of course you can say that we still haven't used the full force of the hypothesis. We only plugged in r to be a constant and we took r equals x power 1. What about other polynomials? What about r equals x square, x cube? What about 1 plus x square, and so on? Now it turns out all of those don't really add any more information to this mix. Okay, so if a function f satisfies these two properties, that it's a linear transformation makes the diagram commute, then it automatically ensures that it is a R linear map or a homomorphism. Okay, meaning all the other R's can also be pulled out. So let me just state that as my final conclusion. Okay, so f from V to W is a kx linear map. So I am now using the alternate terminology for homomorphism. So I'll keep switching back and forth between these various terminologies. F from V to W is a kx linear map if and only if f satisfies two properties. Number one, f from V to W is k linear. In other words, it's a linear transformation of E is a linear transformation of these vector spaces. And property 2, it makes the diagram commute. The diagram commutes. What diagram? The one that I just drew. Okay, V to W, V to W, F, T, S. This diagram commutes. Okay, so I claim that this is if and only if. So I have shown one direction. Now I leave it as an exercise for you to show that the reverse is also true. Just having these two properties is enough to ensure that this map will actually be kx linear. Okay, and to do that you really have to show if x, you can sort of pull the x out, then you can also pull out x square, x cubed, x power 4, and so on. Okay, it's the same sort of theme we have seen before. Okay.